Right, very well. Um, uh, Let us proceed from where we left. Uh, we're going to be looking at the next plot, which in this case is concave downwards. And we want to give a typical case in which this is log kx over kh, the ratio of the rate constant, and here is the plot of the sigma values. So what was observed is that when there are negative rho values, you've got a very small rate, and then with as you're adding the electron withdrawing groups, the rate continues to go up until a certain point, and then as you continue to put electron withdrawing groups, extreme ones like the cyanide and the nitro group, then the rate suddenly begins uh, to go down. So it means that this is a negative plot, this is a positive plot, still on the same plot. On the same curve. So in this case, this is the reaction they were studying, whereby there is an aromatic group, and then now the AR is the aromatic ring with the X at either the para or at the meta position. Yeah. So in this case, it's being done in sulfuric acid. Uh, Perhaps I should. This was water, H2O. Yeah. Sulfuric acid. So it's a mixture of three solvents: sulfuric acid, water, and acetic acid. Yeah. ACOH, that is acetic acid. And then they were actually forming this product. Now the known mechanism for this reaction is the fact that there is this ring, and then there is the protonation. Protonation of the hydroxide is normally fast, and then it gives the protonated water, and then it appears there's a rate determining step in which the water leaves to give a carbocation, and then that carbocation is attacked by the phenyl group, which is nearby, to form this ring which has got a positive charge, and then that loses a proton to form the final product. Yeah. So this is the mechanism. Yeah. So what has been seen is that uh, when you're dealing with aromatic systems, there are the loss of the leaving group to form the positive charge next to the aromatic ring is normally a slow process. So that one is likely to be, that's going to be like a rate determining step. And then it appears as if, and in this rate determining step, what is happening? Yeah? What is happening in this rate determining step? The electrons are going out of the reaction center. This is our reaction center, yeah? The one which I'm circling. That's our reaction center. The one which I'm circling. That's our reaction center. So the electrons are going out of the reaction center, so you'd expect a what? So the electrons will be going out of the reaction center, and then in this other case, uh, once you've gotten the ring here, once you've gotten the carbocation, there is the what? Then there is the ring which is attacking the positive charge here. So this is the overall plot, and then so the scientists were now trying to understand the case, and what was suggested as the way forward was the fact that the mechanism is the same, but then there are two rate determining steps. Yeah, there is the rate determining step 1 or whatever, and this is another rate determining step. Yeah. So what it is this is that is that for this rate determining step, what's going to be happening? The electrons will be going away from the reaction center. So it means that the ones with the extreme sigma values are going to do what? Are going to destabilize that transition state. And this one here, which is has got a positive charge, and the electrons will be coming in. The electrons are going towards the reaction center. So the groups which will be electron withdrawing are going to do what? Are going to be stabilizing. So you've got two areas here, and you've got to see each of these rate determining step. Which side of the plot does it correspond to? So the ones which are what you are seeing is this: is that can you look at this and see that both the negative sigma values and also positive sigma values, they all end up doing what? Having very low rate. And then the one whereby there is almost unsubstituted aromatic ring, it has the highest rate. So in this case, you've got a case of two raw values cancelling one another. So in this case, you've got to see where the rho is increasing, it should correspond to the second transition state, because that's the area in which uh, because there is a building up of what? Of a positive charge, and in that transition state, electrons are going in. So if you're going to have things like the methoxy, the methyl, they're going to destabilize that group. So in this case, the one which I'm showing as rate determining steps 2 corresponds to this area in which the strongly electron donating groups are going to have the lowest rate, and then the one of the electron the mild electron donating groups are going to have the highest rate. And then still in the same reaction mixture, uh, you've got this other case whereby you are developing a positive charge, in which what? If you're developing a positive charge, the strongly electron withdrawing groups like the nitro groups are going to destabilize that positive charge. So this rate determining step 1 corresponds to this other region here. So in this case, what we are doing is we are saying the mechanism is the same, but there are two rate determining steps within the same reaction, two rate determining steps. So when you're going to have a concave down plot, what it means is that there is a change in the rate determining step, but the mechanism does not change. But when you're going to be having concave upwards, then the mechanism changes. I hope you'll just be able to know that. That when you're going to be having what? Concave downwards, the mechanism is the same, but there are two rate determining steps. Okay? Yeah, so in the examples and in the tutorial questions which are excuse me, which I had given earlier to ISO, you can be able to look at the examples which are solved. I think there are some on the Hammett plot. You may be seeing other examples. Yeah. So I think that's the much I'll talk about these deviations from linearity. So we are just remaining one last topic. And this one is on kinetic isotope effect, and I think that's a fairly short topic, and I think I'll just be able to stop there, and then we look at the one on the kinetic isotope effect, yeah, and then we'll be through with this topic. Then the next major topic it is going to be pericyclic reactions. Okay.